The button has been hit. Oh, when in doubt, turn it off and turn it on again. That is the answer. Ladies and gentlemen, I apologize for the delay. OBS once again struck. So, for those that are joining us, this is a office hours stream for this website here, pwn.college. It is free and open to anyone to check out. Just go there, pwn.college. As it says right here, you can learn how to hack. It is a educational website where you can learn kind of the lower level system security related things in computer science. It is used as the infrastructure for a series of university courses at Arizona State University. How does this whole thing work? Well, you can click on dojos and you'll get a list of kind of martial art style progression. This particular stream is focused on software exploitation. Once you click on the topic, such as software exploitation, you can go into a specific dojo module or a specific module. This class is right now talking about dynamic allocator exploitation, or the Heap. You'll find a number of pre-recorded lecture videos along with slides that discuss the topic. Then you have these challenges here. This is live and interactive, so you can launch a challenge by clicking practice. You will then see a little pop-up here that says we have started. There it is. From there, we can go to Workspace or Desktop up here at the top. Workspace will give me a VS Code-like interface where I can interact with that challenge. Let's see if I remember. I will never remember how to open a terminal. Yes, Control-Shift, backtick. And so now I have a VS Code-like interface that I can work on in a live kind of Linux environment to tackle this challenge. If VS Code is not your speed, you can use a live interactive desktop, which is in that same environment. So we can use GUI tools such as IDA to then work on challenges. And if you are like me and like the terminal, we also support SSH. So you can, if configured, SSH hacker at dojo.pwn.college. And if everything is set up correctly, this will give us an SSH session into the challenge where I can also work. Creating an account is free. If you are interested, check it out. So this stream is, we're talking about the Heap. I polled the class and nobody really wants to talk about anything. Somebody says, well, all the guys are here. Are you not in the classroom? There are people in the classroom and on Twitch. They will punk me on Twitch, even though they're here in person, which is always good because it's always interesting to see how quickly I catch it. So we were talking about the Heap. And this module is kind of unique in the sense that all of the challenges just say, all of the later challenges at least, perform an advanced Heap exploit to obtain the flag. And so there isn't a lot of kind of hints to go off of. And the kind of guiding principle here is to check out Shellfish How to Heap, which is a repository that shows various Heap exploits, kind of POCs or proof of concepts of how these exploitation techniques work. And then look at these to figure out what you need to do for these challenges. Because they all say the same thing. And so, for example, and this is not the case as far as I'm aware, House of Spirit is a specific technique. We could open this up, read how this works. We could run this file. And this technique may be the technique that's needed to solve, say, level 6. Right? The problem is that this is a proof of concept, right? This isn't an exploit that I can just kind of copy and apply, right? I can't just upload it onto the dojo and run this and it will get me the flag. So we have to kind of reason about what's going on here. So my plan for today, since nobody said, hey, do this, is I'm going to run one of these on the dojo. And then we will use my kind of toy example from class to then apply that exploit. All right. This won't map one-to-one to a challenge, but it'll be close. So I did prepare a little bit here. I made Heap O, except now it ends in an H because it's office hours, right? I thought it was pretty clever. You may not, but I enjoy the little things. Okay. This is our C file, very similar to what we had in class, slightly modified because I now have this cool read function, right? But other than that, we just malloc and free. Now, the challenges themselves will be slightly more complicated because it may be tracking whether or not an allocation exists or has been freed, if it's been stored. I'm not going to add those restrictions, but we can still function as if those restrictions exist. Will be the way that I'll put it. So the thing that I will look at today, I have how to heap in here. Right? I SCP'd it on up into my dojo instance. You can do the same, right? I don't know, has anyone ran any of the how to heap? Yes? Did you update libc?
Yeah, we did patch buff stuff.
All right, good. That's a common gotcha. Is people will upload how to heap here.
Because when I did into it, one of the exploit broke. I was like, what?
Yes. So this how to heap folder right here is the same thing as this repository right here, just so we're all on the same page. All of the challenges in this module work on glibc 2.35. I see something from Twitch. The camera thinks you're a monitor. Yes, it does. The camera will look at anything other than me, right? Like anything other than what it's supposed to look at. And I'm not entirely sure why. So what a lot of people will do is you'll go into like glibc 2.35 because that is what the dojo uses. And you'll just be like, okay, great. I want to look at House of Botcake. And you'll build this with GCC. We should now have an a.out file, which is that file. And so then we want to like think about this. How to heap glibc 2.35. And so we'll open up House of Botcake, which I just learned maybe, I don't know, 20 minutes ago. This is, do you know where the name comes from, House of Botcake?
House what?
Botcake.
Botcake.
Botcake. I just got a history lesson on this maybe 20 minutes ago. So who do we know that has bot in their name? Kylebot. So Kylebot is actually the author of House of Botcake, which Kylebot is also the maintainer of How to Heap, if you were unaware. And the cake part is part of some inside joke where like they were going to call it House of Pancake. And so they smashed his name with Pancake together in here we are, House of Botcake. And so a good way to kind of reason about these POCs is have the source on one side, run it on the right. I personally, and this is a me thing, you guys can tell me if you agree or do not agree, really have a hard time reading these. Do you have a hard time reading these POCs?
Like the source code?
Yeah. You're like, good?
Yeah,
okay. All right. So maybe it's just me. That's fair. That's fair. So I don't think this one is too bad. But one of the things that you'll see, and this isn't specific to How to Heap, but just in general, when you're looking at kind of heap exploitation, people talk about it, is you'll see a lot of times like this previous value. It's probably what, an int pointer? Yeah. So it is a int pointer, but then we index into it as an array, and in this case, we're indexing it negative. What is happening there?
You're reaching back before the pointer in memory to edit like a size variable, I think.
Right. So, and to me, that's not very intuitive at all, right? When you're first like trying to learn the heap. So we malloc this pointer, and then we just say, okay, this is an int pointer, and then we're going to treat it as an array. So the immediate access of it would be the first value of the allocation, or it could be a next pointer, right? Accessing that pointer with the second member of the array, so index 1, for a big heap would be a previous pointer, right? And then the index 2 would be a next size, index 3 would be a previous size, index -1 would be size, and then index -2 would be
Is that not previous size or?
previous size, right? But previous size isn't always there. But if we're accessing a pointer to an allocation and going 16 bytes back, what we're probably targeting is the previous size value, and we're functioning under the assumption that there is, at least conceptually, a chunk that is behind that pointer. Right? Whether or not it's really there or not is to be seen. One of the common themes that hopefully you encountered in the previous module with Tcache, or 2 modules ago with Tcache, was creating overlapping allocations. Right? That same theme exists here in the big boy deeper heap. The common one being House of Spirit, and I believe House of Einhajar also. If you look at them, they talk about creating allocations, and then they are creating, let's see if I can find it here. We're creating a fake chunk. And so we start writing metadata here as if there were a chunk, right? And a lot of the times the way that you do that is via like an overlapping allocation or changing metadata such that you're accessing a location to like create a chunk out of thin air. Right? Okay, ramble. So we have House of Botcake, and you do this, and you're like, this is great. I'm on glib 2.35, and this is fantastic. How do I know if I'm actually running on glibc 2.35? I compiled this thing. I hit ./a.out. I'm in the 2.35 folder. Kylebot clearly made this work for me, right? Now, but how do I know that that is the case?
LD.
I can use
LD command.
LDD. And what this will show is how these are being resolved. And so we see here that libc is being resolved to this guy right here. And if we run him, we'll see this is 2.31. Turns out you can run libc and it'll tell you the version, if you didn't know. And so this isn't linking how I want. And what was mentioned earlier, run it and see if it fails. Yeah, but sometimes it doesn't fail, right? It didn't fail. Everything worked. And it's one of the things you'll find with heap exploits is techniques may work, or there might be like very minor adjustments across various versions of libc. And so just make sure that you got it right here. So instead, let's look at make.sh, which uses this patch elf command that was mentioned. What we can do is we can compile the file with GCC. I'm using G, so I have debug symbols, but it really doesn't matter. And then call patch elf. And there's 2 things that we need to replace if we're going to update libc, generally speaking. We need to replace libc itself, and then we also want to set the interpreter, which is the loader, though it tends to be tightly coupled with libc. And so if those both are not set, you may have problems. So make sh is pretty boring. If we run make sh on how to heap glibc 2.35 House of Botcake, I get a beautiful a.out. And if we run LDD on this, we see that I have patched this such that libc is now this /lib /libc.so.6. And that is this right here, which is libc 2.35. Right? There are other ways to deal with it. However, I find this to be kind of the most straightforward or direct. So, has anyone taken a look at House of Botcake by chance? Right? Your current instruction is just kind of like look at one and then be like, "Hey, what's going on? Figure it out." Right? So let's do that. How to heap glibc 2.35 House of Botcake. I don't care. All right. It says this attack can bypass some restriction that was added. It has a link to libc source, and it says you can simply double free a victim to do a simple T-cache poisoning. Okay. So the first thing that I want to know when I look at these is what primitives do I need to have? When I say primitives, do I need a free? Like, do I need to be able to free things? Do I need to be able to malloc things? Do I need to be able to double free something? Do I need to be able to use after free? Do I need to be able to overwrite a freed pointer, right? And directly overwrite metadata, right? Well, what is the thing that I need to have? And one of the other things that I learned like 20 minutes ago, which we mentioned a little bit before the stream, is there is, which link is it? There is a sweet website, this one, that is linked on the GitHub page that does exactly what I asked you to do, right? Which is unfortunate, but like if it exists, I'm not going to hide it from you, right? So what libc are we using? 2.35. What primitives do we have, right? And so your job when you're doing these challenges first is just, okay, well, what primitives can I do in this challenge? And as you select the things that you can do, it will tell you which techniques apply. Now, hopefully, you can do this manually, but if you decided to use this tool, I wouldn't blame you. Somebody says something about pwn init. I prefer pwn init opposed to patch elf. It does things automatically. I like simple and straightforward ways. There's always other ways. And we see here the only thing that House of Botcake requires is a double free, which is what's being described up here in our comments. Do we know what set buff does at this point? We've probably seen it in a bajillion challenges. Anyone?
Because if you write the standard exam, normally like malloc something to do.
Yeah, so standard in, standard out are backed by IO files, which are buffered, typically line buffered, right? And we just don't want to deal with any of that. If a byte gets written, we want to get it. And so you frequently see this in CTF challenges or POCs like this. All right. And now it says this file demonstrates the powerful T-cache poisoning attack by tricking malloc into returning a pointer to an arbitrary location. In this demo, it will be the stack. This attack relies only on double free. Okay. It's going to then tell us, I'm doing the same thing in two windows, which is not particularly useful. And we see on the left-hand side is our source, right-hand side is it running. The target address is, and it is some stack variable, and it prints it out right here. And this is how I'd recommend kind of reasoning about what's going on. It's just kind of side by side. We then say, preparing heap layout, allocating 7 chunks to fill the T cache. This is going to be a common pattern if we're dealing with small allocations and we're interacting with something deeper in the heap. We need to malloc 7 things. What is the significance of this hex 100? Does this need to be hex 100? Will it work if I make this hex 8? Do we know yet? We don't know yet, right? We don't know. We don't really know what bins we're interacting with. We just know we're filling the T cache. So
hex 100 would avoid fast bins, right?
So hex 100 does avoid fast bins.
But like, we don't know if that's important.
Right. We don't know yet if that's important. Okay. So then we malloc our 7 to fill the T cache, which aren't particularly interesting. We malloc this previous pointer. And then we say allocating chunk for later consolidation, and we print out our previous pointer. The previous pointer is somewhere over here. Right here, we get the address, and we also get the address of this victim chunk. And so we've, in total, malloced 9 times here. 7 to fill the T cache. Or no, does mallocing fill the T cache? No. Right? When we say fill the T cache, we're thinking ahead of time about what we want to do with these chunks. So we have 9 chunks or 9 allocations of size hex 100. We then do a malloc of size hex 10. And it says allocating a padding to prevent consolidation. What would we call this malloc? It says that it's there to prevent consolidation. It is a guard, right? It is there to make sure that if this last one here I think we called it victim in this code. No, it's called A. Because why would we call it the victim chunk in what we print and victim in our code? That would make too much sense. So A/victim, if we were to free this, since it is the last thing that was malloced, the next chunk is the wilderness. And so if we were to free that, it immediately would get consolidated into the wilderness like we saw in class. And so we have this guard right here. Of size hex 10. Is the 10 significant? No. It is literally just that it is an allocation. What is Twitch saying here? So you can exploit with Botcake without a heap leak at all. Wow. I don't know. We haven't gotten there yet, man. This particular print is also wrong. It doesn't actually do what it says it does. Nothing related to the stack or stack bar. I hope KyleBot is watching. Right? And if he is not, and you have a grievance, submit a PR. Please. Oh, yeah, somebody else says the exact same thing. They beat me to it. Yeah, they're confused when they saw this, but they're too lazy to make a PR. Exactly. It was confusing and hard for me. It's going to be confusing and hard for everyone else. Why try and improve in a public open source resource that everyone depends on? Okay. So, what does it say now? So far, we have 9 allocations. 9 allocations of size hex 100, and then we have a guard allocation at the end. Does everyone have a mental model of what this looks like so far? Cool. Well, one thing that is helpful, this one is not particularly complicated, is to draw out chunks, right, on paper. Like I legitimately did that pretty regularly when I was learning this. But if you have a mental model, we can skip that fun. Okay, so now it says we are able to cause whatever to happen, cause chunk overlapping. We free 7 allocations. What are we doing? We're filling the T cache. It says it right there. That makes sense. This is the only part that's really interesting. Like everything that I've said so far, hopefully was just like, why are you saying this, Robert? Okay. So step 2, we free the victim chunk. So it will be added to the unsorted bin. Then we are freeing the previous chunk. Why do we free the previous chunk? It says it right here. Well, what happens when we free the previous chunk? If you can read, you can tell me. Oh, we got this. Yes, it consolidates, right? It's that same thing that we're avoiding with the victim chunk. We don't want the victim chunk to consolidate with the wilderness. That would be bad. But what we do want is we want the previous chunk and the victim chunk to consolidate. Why do we want that? I don't know, man. Kylebot says it's great. So that's clearly what we want. All right, so we'll leave that as a question that we'll poke at here in a few. So we freed the victim chunk, which is free A. We freed our previous chunk, which caused this consolidation. And then step 4 here says, and I don't like the way this is worded, add the victim chunk to Tcache list by taking one out from it and free the victim again. So that's a word salad. It's probably correct. But really what we do is we call malloc and free. Okay. Where does this free end up? This free A. I can't highlight this. I changed the way my config worked, and now you can't see the colors. I am selecting the line of free A. Right? Where does this free end up? What bin and why?
We end up in small bins.
So somebody said small bin. Somebody says Tcache. Any other bins? There's like 3 others we could guess. Right, it said someone's got to be right. Twitch says Tcache. So we could look at this with GDB. And what do we got here? Disassemble main. What do we want to break? Oh. Fancy, this is why we compile with debug symbols. Where are we interested? We are interested in the word salad. And the word salad happens.
Step 4.
All right, step 4. So this is right around here. What line is that? Step 4 is line 58. So we can break at, what is this? House of Botcake. This is a gamble. We'll see if this works. Line 58. It does. We run. We are now right there. And that worked because I compiled with debug symbols. We are now right there. What are we interested in? Well, the state of the heap bins, right? We have 7 things in the Tcache, which makes sense because we filled the Tcache. Our unsorted bin has 1 chunk. Does that make sense with what we understand so far? Yes. Now, everything that we allocated was size hex 100, right, aside from our guard. So why is this chunk size hex 220?
Because 2 chunks got mashed together.
All right, 2 chunks mashed together, but 100 plus 100 is, in fact, 200.
You gotta have 16 bits bytes for metadata stuff, right?
Right. But there were 2 chunks that were size hex 100 plus 16 bytes for metadata, which would be the chunk is hex 110 despite the allocation being hex 100. And so when these smash together, the chunk size of the consolidated is hex 220. All right, so far so good. Now what we're about to do is malloc hex 100. Where will this malloc hex 100 come from? Where is it going to pull from? What bit? And why?
Just gotta go to unsorted bins first and crack that in half.
So somebody says unsorted bins, and it's going to crack that in half. Any other takers? No takers.
Wait, no, Tcache.
Yes, Tcache, right? Despite this being the module that's on the larger bins, Tcache is just this like ever looming thing that is in front of all of these other bins. And so the purpose of this malloc is to reduce the size of this Tcache because the count is currently 7, the Tcache is currently full. So when we malloc, get past there. We look at our heap bins. Our T-cache count is now 6. The unsorted bin is unaffected. All right, so far so good. Now, the next thing that we're doing is we're going to free. And we're going to free A, which is the pointer that was already freed.
That's in the middle of the unsorted bin chunk.
Okay, so the comment from the class was that this pointer exists in the middle of this unsorted chunk. And that is correct. Let's see if we can print this guy plus hex 220. So this unsorted chunk goes from BA10 to BC10. And what we are trying to free is BB20. Now, because this is a POC, and we are on the correct version of libc, this free should work. Where am I? Bam, bam, bam. Okay, let's go next instruction, and so we're about to call free, and once we do, we see that we didn't blow up. Maybe I can hit R on my keyboard. Free returned 0. And so free was successful. Where did that pointer go when we freed it? To the T-cache. Why?
Because it's not full.
Because, okay, so the T-cache is not full.
And it matched the chunk size.
And the chunk size matters, right? It just that it's the same thing. So this was our pointer that we're freeing a second time. The important value is going to be 8 bytes behind this, which is the size. Let's examine 2 giant hex, and we will go 16 behind it, which is this hex 110, right? And so because the size value behind the pointer that we're freeing is 110, does this last 1 matter? Right, it indicates previous use, so that last lowest 1 doesn't matter. So of this chunk of size 110 being free is what free interprets it as. And when we look at, if we scroll up a bit, the state of the T-cache here, maybe, I typed too many things. Heap bins, we had, this was 6, and so 7 is max. When we free this other thing of size hex 110, it's going to go into the T-cache. And if I remember right, that is kind of the end of the, I don't know. It says, hey, now we have overlapping primitives. Does this actually malloc them back? This is why I hate reading these things. Previous size is, yeah. See, and this is lame. This is why I don't like. Sorry, I was ranting about this for like 20 minutes before I came up here. So right here, what are we doing? We have, it says now we have these chunks are overlapping, and that's our primitive. That's what we've gained, and that's true, right? Does everyone here immediately know what I can do with overlapping allocations? Why does this matter? I got some faces that were not confidence builders, right? That's okay. Someone says GDB it. All right, the answer to everything is GDB. I agree. But this right here, what is this doing and why? This is grabbing, this is cheating to me, okay? Because this is grabbing the size value of the previous chunk that was merged in, right? But it's just grabbing it from memory. If I'm trying to use this as an exploit, do I have the ability to just arbitrarily access this memory location that is behind this pointer? No, I don't. And that's why these are frustrating, because you look at this and be like, yeah, they just get the pointer and go -1. I can do that in my code, right? And the answer is no, you can't, right? But you know what you can do? Can I get that same value? If I were outside of this, how can I get that value? Does anyone know what that value is going to be? Let's start there. The answer is on the screen. So we have one taker for hex 110.
No, it's 100.
Hex 100. Right, so this is why drawing is useful, right? I know it sounded like, yeah, Robert, draw a picture, right? But really, it is. I don't know what's going to happen here with the camera, so this will be a gamble. So I don't care about the T-cache, right, for this. We'll just, T-cache is full. There's really only 2 chunks and 2 pointers that matter, right? We had previous. Poor Twitch. Forever doomed. And then we had A/victim. Right? This right here was hex 110. And this right here was hex 110. Cool? So far so good. Except I'm a liar. This is hex 100. This is our metadata, because remember, what does previous point to?
Size.
The allocation, not the chunk, right? And so this is hex 110, and then this right here is hex 10, right? So our 16 bytes for our metadata. And we have a similar thing going on over here. It's all over. You'd think a university would have whiteboards that work. Maybe. Cool. So then right here, this is our hex 10 metadata. And then this right here is our hex 100 allocation. Right? And I like to think of it that way. Right? We have allocation, and then we have our meta. Cool? A victim is pointing to right here because that's our allocation. So what we did was we had the unsorted bin. We freed victim, and it was chilling there. Then we freed previous, and these merged together. What happened to the metadata of previous? So the metadata used to be that this is a chunk of size hex 110, right? Well, what happens when they consolidate it? We see that on my screen here. It's in the unsorted bin, and it has a size of hex 220. So our metadata here says, hey, this is now hex 220. And for all intents and purposes, from the heap's perspective, does a victim exist? No, a victim doesn't exist. Instead, we have hex 10 for the metadata, and then this whole thing is now hex 210 for a potential allocation, right? It's a chunk of size 220, but if we were to think about it in the same manner, we have hex 10 for the metadata and then hex 210 afterwards. And previous points to right here. So previous -1 is the size of the consolidated chunk, which is hex 220. Now, victim doesn't really exist as far as the heap's concerned, but it's still a pointer, and we freed it again. And so this pointer now exists in the T-cache as a separate chunk, right? And so if I were to write, for instance, from previous, and I fill this up with hex 210 A's, would I see that at this pointer from victim?
If you filled the entire thing.
If I filled the whole thing, I would see those A's. That's what an overlapping allocation is, right? Now, we haven't used it in our GDB stepping through here yet, right? Hopefully that's what The rest of the POC does. But the point is that within this, all of the heap thinks that there is a separate allocation inside of this. Right? And then this would be our meta, and this is our allocation. Right? And so this is a super powerful primitive to have, because I now have the ability from previous to overwrite the metadata here. Right? Where previously we were like, okay, you can buffer overflow into stuff, and this is great, and it's all on the stack, and everything's in line. But a lot of the times we're dealing with dynamic data. And here we had to create that scenario where previous is now a location that's early, a victim is some location that's later. From writing to previous, I can overwrite what the heap will think is going on with victim. Now this isn't, okay, so previous is unsorted. It's big boy heap, right? So it has, what is directly at previous?
The next pointer.
It's a next pointer. Okay, we've got next. What comes after that?
In the T cache, would it be the key?
Is previous in the T cache?
Oh, no, yeah.
Previous is in the unsorted bin. So previous does have a previous pointer. Cool. A victim. Where did we free that to?
The T cache.
The T cache. So what is right at a victim?
The next pointer.
The next pointer. There's always a next pointer. Yeah, we like that one. Is there a previous pointer?
No, that's where the key is. Oh, it's right in the bytes.
Correct. So we'll keep my horrible drawing here. And so we have the next pointer, then we have our key, because this is a T cache chunk. And so what we've created is a T cache chunk that is inside a heap chunk. Cool. So my original question was, what is this previous -1 getting and why?
Yeah, it's getting that 210 or 220.
It's getting the 220 that is the size of previous. Can I figure out what this is, what this number is, without accessing it directly?
You just do the math.
I can do math, right? Like there was another point of conversation earlier today was people were like, but I don't want to do the math. I can just use some fancy tool. I can brute force it. I'll write a for loop, right? Like that. That's baloney. Okay? This POC is just like, oh yeah, well, you can just access it. But if you're trying to use this exploit, you can't just access it, and you have to do the math. So I don't understand why the POC doesn't just do the math, right? It's going to be hex 100, which is this allocation, plus hex 100, which is this allocation, plus 20 bytes, or hex 20 bytes for the metadata. The number is going to be hex 220, right? Now, will it always be hex 220? Answer is no. Right? This depends upon the size of our allocation. This also depends upon the alignment of the heap. Because if you'll recall, way back in a Jan lecture, there is a scenario, although I don't think you can do it on 2.35, where the previous data overlaps with the end of the previous chunk.
Yeah.
Right? And if you are doing a heap-related exploit, then your metadata isn't always going, where that is the case between your two chunks, then your metadata offset here isn't always going to be hex 10. But it will be deterministic, which means at a bare minimum, you can do what we just did here and throw GDB at it and be like, okay, that's the number I need. But you could also do the math, and hopefully you understand where these numbers are coming from. Cool. So this is just grabbing that value, and we just do it via a negative array index and binary and, because that's cool. What is a size getting me? It is a -1 ANDed with FF0.
What time?
Hey, our drawing came in handy. We were getting that hex 110, which is the size of the T cache. Do we know that? Ahead of time? Yes, because we allocated it. So why do we do it like this? That is my question. All right, so then we print off some helpful stuff. What do we say here? We are printing the previous pointer, which we know the size of it. We are printing our victim pointer and the size of it. We then call malloc 100. What do we expect this malloc hex 100 to give us? Right, we haven't done anything else, so the state of the heap is still this. Not the drawing, but GDB here.
That should be shown on our victim chart, right?
So if we hex 100, it is something that's small enough to go to the T cache. Do we have things in the T cache? Yes. The T cache is last in, first out. So it's going to be the most recently thing that was freed, which was victim. So when we malloc, we're going to get back our victim pointer. So there's our pretty printing. We malloc, and then we print A, and that is the same thing that we had. Up here, it is the BB20, which was our victim pointer, the most recent thing that we pushed there. Now it's going to do something else that just looks crazy. Let's see if we can make sense of it. We have memset A 0 hex 100.
So clear out everything that's in A.
Okay, what is A? A is our victim pointer, and we're going to 0 out all of this. Okay, I don't know why we're doing that, but we're doing it.
I think this is proving that overlapping is happening.
We're going to prove that overlapping is happening.
Yeah. Because now we're going to try to write A's into previous.
Does this output X as well?
So we have written zeros all over this bad boy, right?
Yep.
Okay. I'll just trust you here. Then, okay, this is where the weird thing happens. What are we doing? Previous array index of hex 110 divided by size of int pointer underscore t. Again, why? I like thinking about this. That is just madness. Okay?
So theoretically, that should be like the quote-unquote array value of where A starts, right?
So,
Inside
like, I don't even know what the size of an int pointer underscore t is. I mean, pointers should be 8 bytes, right? And so this should be accessing previous by hex 110 divided by 8, which should be whatever that is divided by. I can't even.
Is it trying to do like A's next from previous?
What's that?
Is it trying to get to like?
I know what it's trying to do. It's trying to get to here from previous, which is what you just said, right?
Wow.
But why are we writing it this way? Right? If we know this is a distance, why are we doing a math to compute an index to access a pointer as if it were an array by virtue of size?
We're
Right?
showing future software engineers that analyzing code, you always have to deal with weird things like this.
Like this is why the White House put out a memo that said we need memory safe code, because people write things like this, right? We're starting from here and we're doing the math to get to here, right? To me, it makes a lot more sense to just treat this as a pointer and then add a raw number than access it as an array. But the effect is the same, right? Somebody says, ask CalBot. I had a lengthy discussion with CalBot, and we just agreed to disagree, which is fine, right? It's great. But what we're doing is we are computing the distance from previous to these zeros that we just wrote, and we are placing hex 41, hex 41, hex 41, hex 41, which hopefully we know is Big A. All right. So then there is an assert, which is lame. Like, asserts are cool, but you know what would have been great is if we printed. Yes. If we printed it before and then we printed it after so that one could in fact see it. But you know what's the beauty of having POCs?
Editing
we can edit them. Right? We can edit them and make them make sense to us. So we will print f, and let's do %s, and we will pass it a. Right? And at this point, it should be null. Right? We agree? And then...
Wait, would that print out just like blank space in the terminal?
Well, let's give it before doing fancy prev stuff. Right, so we'll see it. But yeah, it should be a string that just is null, and so it should just be a nothing burger. And then we'll give it a new line at the end here as well. Okay, then we will do this a second time, and we'll give it some fancy text, which will be after doing fancy prev stuff. The assertion's great, but I like seeing things. Right? And we can see it with GDB, so like that's fair. So let's get down to it, and we can examine the string at A. Right? We see it in GDB, but if you are not necessarily in love with GDB like I am, we can build this again with, what was it? How to Heap, glibc 2.35, House of Botcake. And that is a suggestion. And we see here that it was in fact all null, and then we were performing that access from the previous pointer specifically to these right here, right? They used an array index to kind of jump all of this, but we very easily could have just buffer overflowed our happy way from here to there, right? The way that we got to accessing this doesn't necessarily matter. So I said this is a powerful primitive, having this overlapping allocation. So far, this POC just showed us that we can turn nulls into A's. Which, all right. So I have two things that I want to look at here. First is, what else can we do with it other than turn nulls to A's?
So we can write to A while it's free, basically, right?
We can write to A while it's free. Yes.
Because previous overlaps it. So like theoretically, we could overwrite the next value while it's in the T-cache.
Okay. So if we didn't write a whole bunch of zeros here, when it was freed and it was in the T-cache, there was an X pointer here. And so we could overwrite the next pointer. And we could make that point to wherever we want. Then if we were to malloc 100, hex 100, we get our victim. Yep. Then if we malloc hex 100 again, we get whatever we wrote for the next pointer. Everyone agree? Just T-cache?
Wait, but T-cache is full, right?
The question is, but T-cache is full. So let's do it. Okay. So my claim here is
It's full, but our victim was already in there.
I'm going to take this, and hopefully this math works. I'm going to, because the access of whatever that nonsense was, do I want to go one behind it? No, I want to actually go to the same spot. Okay. And I want to do that before I malloc this, right? So this is now overwriting the next pointer of the freed victim inside the T-cache.
Yeah.
We agree?
Yeah.
Okay.
That's second fault.
And I don't necessarily care if it's egg faults.
Yeah.
The point is that we could influence it, right?
Do we want to also not? Well, I guess it doesn't matter if it's in it or not.
Yeah, we can comment that out. That's fine. So we just shuffle a couple things around here, right? Just the order that we are interacting with these pointers. And my claim, if I'm doing this right, is we should see in GDB. We'll make this guy. We will GDB it. Where do we want to break? Let's break at line 73. Which 73 is when this malloc occurs. We run it. And so we are right before this malloc occurs, right? So we perform the overwrite of what should be our next pointer, and we are about to malloc that hex 100. What do we expect to happen?
We're going to get the top of the T cache, which is currently our victim, which is our whatever address speed.
Yes. And the statement was we're going to get whatever is our victim because this is what is at the head of the T cache. And so we'll just get whatever this pointer is.
Can we look at the T cache before we do that?
Yes, we should. If we heap bins, well, now it says some weird looking. Yeah, I don't know. Yeah.
Can we examine that address to make sure that we we're force?
Okay. So this is our address. The question was, can we examine this? Okay.
Cool.
So that looks good. Something else has gone awry though, which was not planned. So we will go through that malloc. So far, so good. Great. Then we heap bins. And Tcache is, Jeff is not happy because it turns out 414141 is like not a good thing to dereference.
Oh, right, because we have safe linking, don't we?
We do have safe linking.
So I tried to demangle that.
And so I tried to demangle 414141 and that went to heck. But we see that we can overwrite the next pointer. And so we also already know how to deal with safe linking. So we could create a mangled pointer, place it there, and deal with it. Yes?
Question I maybe might ask us. Is safe linking not turned on for like small and large bit?
Safe linking is only enabled. The question is safe linking turned off for small and large bins? And I'll also add unsorted bin to there. Safe linking only exists for the bins that are singly linked lists. So you can think of it as there's like 3 different implementations of the heap. There are really 2. There's the singly linked list, which uses safe linking. That is going to be your T cache. That's going to be your fast bins. Then there's your doubly linked list. That's going to be your unsorted bins, your large bins, your small bins, those guys there. Those do not use safe linking. You can still blow up pretty easily, right? I believe I talk about it in the pre-recorded videos where we talk about the unlink procedure a little bit at the end, which is definitely worth looking at. We have time. We can. It wasn't what I was going to do, but we could. Where it doesn't use this like crazy XOR thing, but it does look at the pointers that are used in the metadata of the heap to validate them. And that is another way that the heap will just be like, hey man, this doesn't add up, right? When you start freeing things and unlinking free chunks. There's a separate validation process where safe linking is used in the like fast caching layers, which is Tcache and fastbins. Twitch says, I wonder if that's what they were intending to do with the stack var. Yeah, I imagine that this is what I just attempted and then blew up due to safe linking. Is like the intended approach at one point, if we were to like go through the Git history, is they were going to overwrite this next pointer and then just over time, because these POCs get updated for every libc, somehow as they updated it, it ended up in this kind of incomplete state. And so instead of writing this right here, we'd have to say, note, we need to deal with safe linking. Right? Now that would require that I have a leak of the heap. I couldn't just write some arbitrary thing there. Right? So now my requirement is not just that I have a double free, is it? And so that means that website was a lie. I mean, like, it is, but it isn't, right? You can get, if the primitive that you get is the overlapping allocation, then that is true. But if we want to say, I want to turn this into an arbitrary read or write, right? I want to get an arbitrary pointer returned to me. Suddenly, I also have to have a heap leak because I need that heap leak to defeat safe linking to influence that next pointer, which is kind of an interesting aside there. Cool. Any questions about this so far? There's one last thing I wanted to poke at on Botcake. Right? And hopefully you can do the same thing with the other POCs. That's why I'm doing this, right? I'm editing the code, be like, all right, this is what I think's going on, and let's take a look at it. Feel free to change it, mess around with it, make it make sense to you, because a lot of it doesn't make sense to me unless I do this. Cool. So I'm going to git check out. I'm going to undo all of the nonsense that I just did. So now we have the original source, or the original POC as intended. Now, something that we asked but didn't answer kind of at the beginning of this was, what is going on with step 4? So what we did, to recap, was we filled the T cache. We freed victim. We freed previous. These two merge. Then we have to do this malloc. Do we know why we need to do this malloc? Is this malloc important?
To open a slot in the T cache.
To open a slot in the T cache. What happens if we do not open a slot in the T cache?
The victim thing goes to small bins, or
The victim thing doesn't go to T cache, where we're right there. That's what I want. If we don't do that malloc, then as was pointed out, there is no longer an open slot for the T cache. So then what happens when we do this second free? And remember, the second free here is what gives us this. We fail. And why do we fail? Double free or corruption, exclamation point, prev. Well, that's a different error than safe linking. It kind of goes back to the question of, well, what's going on with safe linking? We don't have safe linking in these other bins. It doesn't go to the small bin. It goes to the unsorted bin. And so when it goes to the unsorted bin, is it going to be a singly linked list or a doubly linked list? It's going to be a doubly linked list. The doubly linked list doesn't do safe linking. Instead, it does this unlink thing that we kind of alluded to. You want to take a look at that? See what unlink does?
Sure.
All right. This is where we're just kind of freeballing. So we'll go to Elixir Bootlin. We're looking for malloc.c. Oops. Elixir Bootlin malloc.c. For whatever reason, I've learned that if I just go to Elixir Bootlin and then I search for malloc, it doesn't show me malloc.c. I don't know why. Right? I don't know how to use the search box, apparently. Now, what I'm interested in is this error message, double free or corruption. So let's double free or okay.
Do we want to be in 235?
Comment, do we want to be in glibc 235? The answer is probably, since that is, in fact, what we are working with. We can still search for that error message in the source. And is this what we got? Double free or corruption fast top? No. What did we get? Exclamation point prev. Okay. See if I can use No, Safari is not happy. It was too much. I have to refresh the page.
Search for
No, like literally the search functionality broke. So, okay. No, we can still search for this thing because there's several hits. It's not fast top. It's not top. It's not out. Hey, it's this one right here. It's this exclamation point previous. And so, how did we get here? What did we fail? Whether or not the block is actually not marked used. And it is looking at if the previous in use bit is set for the next chunk. And the next chunk up here is chunk at offset. Now, chunk at offset, I'll just tell you right now, this is just addition, right?
it's adding size to P.
Yes, it's adding size to P, right? Define chunk at offset, we take P and we add the size. So it hopefully isn't a big noodle scratcher there. So what we're trying to do is we're trying to free A, right? In A, we're looking at the next chunk. What is the next chunk from A as far as the heap is concerned?
Nothing.
Nothing.
Wait, no, what's after this memory?
Well, let's go back up here a bit. And our keyword we're looking for is malloc.
Oh,
Okay, so
guard allocation?
our guard allocation, right? So if we assume that there was nothing, everything was malloc fresh, which I'm going to assume. I don't know that's the case here. We could GDB it and find out. I'm going, and our plot doesn't print our guard allocation. In contiguous memory, which is what our drawing here is, there is a guard allocation of hex 10. That's just chilling right here. Right? This is our guard. And he has a metadata. Right? He is hex 10, so this is hex 10. We're going to assume there's 10 bytes for metadata. What do we have here? Previous size and then size. And what is the least significant bit of size? Or that the previous one is in use? Is that what this is checking?
Yes.
Yes. Now, what is the previous size that's stored up here? I'm halfway tempted to see if this is real in GDB. But we can go with our crummy drawings. I think graphically looking at it is nice as well. So this previous value that is inside the guard. At the time of free A, what is previous size?
This is the first time we freed A.
We've freed A, we freed prev. We're trying to free A for a second time. What is prev size? It's actually a trick question. Prev size isn't there. If I am thinking about it correctly, because prev size is set when something is freed, and the previous chunk to our guard, once these are consolidated, is prev, which is in use, isn't it? Because we've malloced it.
Yeah.
Now, if we had freed it, it would be hex 220. And so this unlink procedure is doing these verifications. It's saying, all right, here's a pointer. Let's go size ahead. Does the chunk that's ahead of us, does its tracking of our state coincide with what we think we're doing? And so what we're failing on here is previous in use of the next chunk. So the least significant bit of the size of the guard allocation does not match the state that this needs to be in to free. We're trying to free A. A is going to look at its size.
Okay.
So it's going to, like, free isn't that bright. It doesn't know that A isn't really a chunk. It just has a pointer, and it's going to say, give me the size, which is going to be whatever is 8 bytes behind the pointer, right? Give me that, add it, check the size of this made up chunk. Does the data there match? Right here, the answer is no. And if we look at this whole blob here of stuff, we're inside free. This is the kind of nasty unlinking procedure where there's a bunch of different pieces of metadata that it wants to check. Does the next pointer of something, this is not related to contiguous memory now, this is related to our list, because this is how we think about things contiguously. But say I had, which is now a completely made up scenario, 3 chunks, and we have next pointers, and we have previous pointers, and it looks something like this. Is this a good enough drawing for everyone? You can't see it, it just sucks to be you. We have three chunks here. One of the other things that it will verify is if the previous pointer of the next chunk points to me. Does that make sense as a sentence? So we go next previous should equal where I am, because I went forward and back. And it'll also verify that back next equals where I am, right? And what that's doing is that is verifying within the list that the metadata also makes sense. And if that doesn't resolve correctly, you'll also get some type of amazing corruption error from this unlinking procedure. And so in order to start messing about with this, and House of Botcake is an easy example, right? We have to think about not only the metadata within contiguous memory, where we're verifying the chunk that is contiguously in front of us, and that metadata, but we also have to concern ourselves with the metadata of the pointers as well. And if that doesn't add up, you'll also explode. And that's where this can become a very fun set of challenges as you think about that. But if you take an approach that is very similar to like the file struct exploits, where there's some pointer, there's some offset, and it has to satisfy this constraint. If you think about it that way, it isn't that bad. Because the heap doesn't actually know like what's a chunk or what isn't. All it is doing is there's some pointer, we dereference it, we dereference some offset, does it equal something else? And so when it gets to this kind of world of can I fake a chunk or create a fake allocation or overlap some stuff, it is still very much like what you saw in file structs, where it's what is going on in the assembly, what are the bare minimum requirements that are necessary to kind of satisfy this, and then can I fake it? Like if I have an overlapping allocation here, and I could get this, I could make this be a fake chunk, I could make up this size, I could make it up to be something big, I could get it into the unsorted bin, and then if it's in the unsorted bin, then there's like this imaginary next pointer, and then there's an imaginary previous pointer, and since I have this overlapping thing, I can fake all of that. And I could make this point to this, which points to this, and I could make this size equal the offset to this. I can make all that work, right? I'd have to draw a whole bunch of arrows, and it would be a giant mess on the whiteboard more than it already is. But hopefully you see how once you have kind of this ability to influence part of the metadata, you can start making the heap think whatever it wants. Now, the kind of gotcha here is we saw that we can explode in the T-cache, right? A lot of the times when you create this like made up environment, it's a one-off. And then it's like, do not touch the heap again, or else the whole house of cards crumbles, right? So keep that in mind, but I don't think that is an issue for anything that's in this module. All right. So that is what I got to ramble about. Does anyone have any questions or something in particular you'd like me to poke at? Other than like, hey, solve this challenge.
How do you know if you have double free primitive? Yeah.
The question is, how do I know if I have a double free primitive? Let's not look at that. Let's look at do.c. Somebody that's not the person that asked, does my do.c allow for a double free?
Yeah.
Okay, I got one yes. I'm looking for 3 answers.
Yes.
I got a second yes. All right, I got 3 yeses. Person that asked, do you agree and why?
Yes, I'm wondering, is that functionally different from a use after free?
Yes.
Okay.
So the difference between a use after free and a double free. Use after free would be, okay. The issue, they're related and similar. So it is a good question. The primary mistake here is that this pointer's index, right, is not nulled out. Okay, that is like the high level mistake that's going on. But there is a difference between the two, because I could not null it out. Okay, but if I added some freed, that's call it in use. I added this, and then when I malloc, we set in use of index equal to 1, and then here I in use index equals 0, and then we'd have to make this exist as an array. Cool. I've effectively stopped double free. If we look at the logic in the code. When something is malloc, I set in use equal to true. I could only free it if it's in use, and once I have freed it, it cannot be freed again because in use is set to 0. So a double free is not possible in this code, assuming that I wrote valid code. However, is a use after free still possible here?
Yes.
Where?
In the read function.
In the read function. So I could malloc something, free it, and then reuse the pointer so I could get access into freed data. That's a use after free. However, I cannot call free on the same address twice. And so they are, in fact, 2 different primitives. Good question. Any other questions? All right, we are going into spring break here for anyone that is not an ASU student and watching this, which means there is no new work being launched for the first Friday of the semester. Hopefully, you guys get to enjoy spring break a bit. Okay, that is the intention. I know we had midterms and other classes, and so people are just kind of tackling this right now over the weekend. If this looks like some impossible thing come Sunday, it makes no difference to me if we extend the deadline of this module to the end of spring break. Okay. So let me know, because what I care about is that we cover the material, not like, hey, let's, oh yes, do it in 3 days. Okay, like that isn't my goal here. But the flip side of it is I'm not going to shift it because I want you to finish it over the weekend and have a week off. Right? That is what I hope happens.
But we will launch next Friday.
Question is the next module, when will it launch? Hopefully, right? It will launch next week, Friday, while you still are on spring break. If you do not look at it at all, that's perfectly fine, right? We'll talk about it on class, which will be, Tuesday? I don't anticipate it being a particularly brutal module. Okay. The intention of this first one here is to just kind of be like, hey, we're working with some different stuff here, right? Let's do some of the things we're familiar with and look at what's different. Hopefully it'll be a easy module in general, right? We're like with this heap stuff, we're dealing with a lot of moving parts. I don't anticipate the first Windows module being particularly complicated, but you know, I could prove myself wrong here. We'll see in 7 days.
Do we need like set up a Windows environment?
The question is, do we need to set up a Windows environment? The answer is no.
Okay.
This will all be solvable on the dojo. That I know works. Okay. The question is, to what degree does it work in practice when students start using it? And so that'll be a little bit of give and take. Okay. This is how most of 494 went last year, right? Like what you're about to experience when you come back from spring break is like, to me, the fun part of pwn.college. All right, because that is where we say, hey, here's something cool and something new, and it may break and it may explode, and there may be like challenges that misbehave, and you're going to be like, Robert, this is broken. Why didn't you do this? And I'm going to be like, oh, right. Let's fix this, and it's going to be hopefully fun for everyone, right? Where what you say will help influence what we talk about. Right? I try and do that with office hours, right? Where I say, hey, what are you interested in? What are you stuck on? What are your questions? And incorporate that. The entire module becomes that and how we build this stuff kind of going forward, right? And if things blow up, it won't be on you. Like, I will own that and be like, all right, it's my fault. You guys couldn't do this for like 3 out of 7 days, and we'll fix it, okay? But hopefully everything goes off without a hitch, as we are known for. They will be nothing but utter perfection, and it will be challenging and difficult, and you will continue to be challenged. But either way, hopefully you'll learn something. With that, I will let everyone go. Twitch says nothing. Enjoy spring break. There will be no streams for 7 days. Goodbye and good luck.